Hello, everybody. We're looking right now at the first section of the topic 10 notes. And what we're going to do today is we're going to split this part into two. We're going to split it into two chunks. Okay, the first chunk is going to be a bunch of information that's sort of introductory to the entire unit. Sort of a lot of background information, and hopefully some of it is actually just review info that you've seen before. But we're gonna look at some background information about just like an overview, sort of laying a foundation for what we're gonna do, and then at the end we will get into some specifics about what is on your problems for today, your actual Canvas assignment. Okay, so first let's talk about trigonometry. Okay, that's what we're studying. That's what the general topic for Unit 10 is going to be. Trigonometry is the geometry of triangles. And most of the time when you're talking trig, you're talking right triangles. So the key feature of that, of course, is the right angle. Well, one corner of a right triangle is a right angle, 90 degrees. That's actually what defines what is a right triangle, is if it has a right angle or not. And the other parts, and I want you to go ahead and label these on your paper. The other parts of a right triangle that we're going to be talking about are the legs. Okay, the legs are the two sides that make that right angle. And then the third side, the longest side, is the hypotenuse. All right, so you've got the right angle, the legs, and the hypotenuse to go ahead and label on your paper. Okay, that's what we're going to be talking about. Up next is hopefully something that you've seen before, because I'm pretty sure this is taught a little bit in 7th grade and a ton in 8th grade, and probably some in Algebra 1 as well. Okay, this is pretty standard stuff for middle school math. The Pythagorean theorem, everybody knows this equation. A squared plus B squared equals C squared. We all have seen that before. Okay, so when you're looking at that equation, A and B are the legs of your right triangle, and C is the hypotenuse. And so this relationship exists for every single right triangle that there ever was created. Doesn't matter how long A and B were, C always ended up matching this equation right here. And so we have an example problem that wants us to solve for X. And you can see it on here when you're trying to solve for X. You can see that we've got a right triangle, and you can see a couple of the measurements that are given to us. And you know that if we're using this right triangle, we're using the Pythagorean theorem, then the leg squared plus the other leg squared equals the hypotenuse squared. Well, that's x squared, 7 squared, and 14 squared. So what we want to do is get x by itself in this equation, right? So what we can do is just subtract that. We subtract the 7 squared over to the other side, and you can convert those to regular old numbers. You don't have to leave it as 14 squared and 7 squared. But either way, whenever you do that part of it, you always end up right here where x squared equals 147. So here's what happens. We are on the left side of that equation, we are multiplying x times itself. So we've got x squared, but we don't want x squared. We're not interested in x squared. We want to know what is x, just the one x by itself. And so to undo squaring it, what we do is we take the square root on both sides. Okay, we take that square root. What we're doing is that right there, and you can see the radical. That little square root symbol is called a radical. The radical and the exponent undo each other, and we're left with just x by itself. Now, square root of 147 is a different animal altogether, because in previous units, what we've done is we would just type this into a calculator and get a decimal approximate answer. Okay, square root of 147, if you type that into a calculator, gives you 12.124 if you're going to round that off. And that's what we would do, and all of your answer choices on the assignments and tests and stuff all had those decimal answers. Well, we're not going to be doing that anymore starting today. What we're going to be doing is simplifying these square roots and leaving stuff in radical form. And I mean that leaving it in terms of a square root. Okay, so take a look at this. I want to call your attention back to about 5th grade now. And I want to call your attention back to a factor tree. Okay, a factor tree is something you probably haven't thought much about since you did this back in elementary school. Well, let's say you had a number like 45, and you know that 45 is equal to 9 times 5. And you also know that 9 is equal to 3 times 3. Okay, y'all will remember this from back in elementary school. And so instead of 45, you could say that 45 is the same thing as 3 times 5. Okay, we are going to do that exact process with the number that's underneath our square root right here, the number 147. Now I'm going to split that into 49 times 3. Now you're asking yourself, why in the world would you split it into 49 times 3? And the answer is, it doesn't really matter how you split it up. There's a couple of different ways you could multiply two numbers and make it equal to 147. But one of the reasons you might want to pick 49 is because 49 is a perfect square. I want to show you something, okay? Something you can do with radicals is if you have a square root of a number like 147, something you can do is split it into two separate square roots. So instead of square root of 147, you could say that it's the square root of 49 times the square root of 3. Now, the square root of 49, this right here, is something we already know what it is because we know that 49 can be broken down into 7 times 7. So instead of writing square root of 147, we could say that that is equal to 7 times the square root of 3. And that's what our final answer is going to be, okay? So just as an aside, if you are not sure, if you're not super comfortable with all of this information right here, it's okay because we're going to have lots of time and opportunities to practice. Starting tomorrow, we will have some practice problems on breaking down square roots, okay? So don't super worry about it. This is just a basic version of that, all right? Let's go on to the next part. The next page is something that will help you as you try to work on breaking down square roots. This thing on the left is a multiplication table. It's pretty simple. You take whatever number on the top and you're trying to multiply it times a number down the left side. You find where those two numbers cross, like you'd say 14 times 12. You see where they cross over. 14 times 12 is 168. All right, that's something you could do to help you break down multiplying numbers and find factors. All of these numbers right here is a list of perfect squares. Okay, a minute ago on this slide, we broke down into 49 times 3 because 49 was a perfect square. 49 shows up on that chart right there. Okay, so any of these numbers could be useful to you in breaking down square roots. And you're going to see more of that on the next lesson. All right. So pause the video and go ahead and write all of those down. I'm going to move on. The next part on our page is Pythagorean triples. This is the last thing we're going to look at in our introductory material. Pythagorean triples is what you call three numbers that satisfy the Pythagorean theorem. That's what that PT on your paper stands for. Okay, a Pythagorean triple is a set of three numbers that satisfy the Pythagorean theorem. There's a whole bunch of them that are listed on your page right here. All of these work. So, for example, if one leg was 11 units and the other leg was 60 units, the hypotenuse would be 61 units. And if you plugged that into a squared plus b squared equals c squared, all of these numbers fit. Okay? However, the three most common ones, what you need to fill in on your paper, are 3, 4, 5, 5, 12, 13, and 7, 24, 25. Those are the ones you need to fill in on your paper. Those three right across the top right here. I want to show you what that looks like, okay? If you had a side length of 3 and a side length of 4, your hypotenuse would be 5. That's what this tells us, that it's a Pythagorean triple. And look at what that does when you plug it in to a squared, b squared, and c squared. You'd have 3 squared, you would have 4 squared, and you would have your hypotenuse 5 squared. Well, look at what that is. You've got 9, and you've got 16, and you've got 25. And all of that checks out, doesn't it? All of that works. That fits with the Pythagorean theorem. Now, the last part is this. If you take any of these Pythagorean triples and you scale them up, for example, if you scaled it by a factor of 2, instead of 3, 4, and 5, you had 6, 8, and 10. It still works. Look at that. 6, 8, and 10, 6 squared plus 8 squared is 36 plus 64, which is 100, and that's 10 squared. Y'all, even if you have those Pythagorean triples scaled up by some scale factor, it's still going to fit in that theorem. All right? So all of that we have written down up to this point, all of that is introductory material. Some of it was review. Some of it was maybe a little bit confusing, like breaking down the square roots, but that's okay. We're going to work on it. There's lots of time between now and when we take the DCA. And the last part was our Pythagorean triples, something that you will recognize here and there as we move around, as we move throughout this unit. Okay, what I want to focus on right now is what is actually on your Canvas assignment for today. Okay, this is what is called a 45-45-90 triangle. Now you're asking yourself, why in the world is it called that? And the answer is this. We know that every single triangle ever created always adds up to 180 degrees. All the angles on the interior add up to 180 degrees. Well, you can see on the picture that this one is a right angle, so obviously that's going to be 90. And the other one that's already labeled is 45. So if you're doing that quick math and you know that it has to add up to 180, you know that this one down here must also be 45. And that's where the name comes from. 45-45-90 triangle is named after the angles on the inside of it. All right? Now, we are not super concerned about the angles in this triangle because, while that's important, it's also kind of obvious given that the name of this triangle is 45-45-90. It's pretty obvious what those angles are going to be. What we are more concerned about is the length of the sides. So the first thing we need to know is that on a 45-45-90 triangle, because of these two angles being the same thing, it makes it to where these legs are the same length also. So if this one that's labeled 8 right here, that means this one is also labeled 8. Okay, this leg is also 8 units long. Now, the last part is our theorem, and this is a formula that says the hypotenuse on a 45-45-90 triangle, the hypotenuse is equal to the leg length times the square root of 2. So if your leg length on this triangle is 8, that means your hypotenuse length is 8 times the square root of 2. Or you could just say 8 root 2, 8 square root 2, something like that. This right here is a diagram that shows it in general. Okay, our specific example had 8, but it works for any number that you give to your leg length. Okay, if your leg is x, the hypotenuse on a 45-45-90 is x times the square root of 2. We've got a couple of problems right here, and these are the problems. These problems right here are very, very similar to the ones that you're going to see on Canvas. The first one, so first off, it tells you that this is a 45-45-90 triangle, and you can tell in this picture, because we've got a 45 down here and a right angle right there, that this one also has to be 45. And we have this formula, the relationship between legs and the hypotenuse on this kind of triangle. And it tells us that AB, this side right here, has a length of 7. If that is the case, and that is 7, this other leg must be the same thing. It has to also be 7. The other one, the other length, AC, is the hypotenuse. Well, according to our formula, hypotenuse equals leg times square root of 2. So all we're going to have is just 7 times square root of 2. It does not have to be some huge complicated thing. It's just 7 times square root of 2. Make sure for your answer you are leaving this in square root format, Okay? Leave that in square root format. The square root of 2 is a never-ending, it's what we call an irrational number. It's a long, never-ending decimal with no pattern and no repeating and stuff. And so it doesn't matter how many decimal places you write down, it's always going to have some sort of rounding error in it. So the most exact the most exact and precise way to write this answer is leaving it as a square root right there. Take a look at our last problem. Last problem for today. We've got this time AC. Well, AC is our hypotenuse, right? So if the hypotenuse is 8, we know that our formula says the hypotenuse equals leg times 2, right? Put that into a equation. The hypotenuse, 8, equals the leg, our unknown, times square root of 2. Okay? Think about what's happening to x right here. X is being multiplied times the square root of 2. And what I mean by that is we've just got a little dot multiplication right there. X times the square root of 2. So the question, how do you undo multiplying something? And the answer is you divide it. Divide both sides by square root of 2. Don't get thrown off just because it has a radical attached to it, okay? The square root of 2 is just 1.414. Okay, if you were doing 1.4 times x, you know that you were going to divide it. So why would it be any different? Okay, that square root of 2, just because it has a radical, doesn't mean you can't treat it like any other number. Okay, so that's how we end up with our answer, 8 divided by square root of 2. That's what our leg length is, 8 divided by square root of 2. And the other thing we know about these special right triangles, these 45, 45, 90s, is that the legs are both the same length. So if you've got one, you've automatically got the other one also. All right, that's all we've got for these for this first part of the notes. We'll get to the rest of them in the next lesson, the next page, and we'll have some practice about simplifying square roots also. All right, y'all have a good one.